before moving on to the consequence of this separation, let us maybe look into one example to see that how the velocity profile gets affected because of it. Let us say that we want to have an estimation of the velocity profile at the point of separation, and let us say that it is given in this form: u by u infinity is equal to a0 plus a1 y by delta plus a2 this is an example of, assume that this is velocity profile at the inception of separation. Our objective is to find out a0, a1, a2, a3 consistent with the physical conditions. So it is just like estimating a velocity profile or fitting a velocity profile in a polynomial form that we did for flow over a flat plate, but the boundary conditions which should be consistent with this one, the boundary conditions are somewhat altered. So what are the boundary conditions that we need to consider for this? Again there are 4 constants, so we should consider 4 boundary conditions to specify the velocity profile completely. So what are the boundary conditions that we should consider? Number 1, at y equal to 0, u equal to 0, fine. Then at y tends to infinity, or at y equal to delta here, which is like tends to infinity, at y equal to delta, u equal to u infinity, at y equal to delta you have no further change in u, and fourth one at y equal to 0 this is equal to 0. This is very very important because this is the hallmark of separation. At y equal to 0 you cannot apply d2u dy2 equal to 0, that was for flow over a flat plate because dp dx was 0. Here dp dx is not 0 because you are given that the velocity profile at the inception of separation, when there is a chance of separation it must be dp dx greater than 0. Now the big question is that why such a separation will occur. See, when the fluid is there within the boundary layer it has some energy, but because of the reduction in the velocity that is being imposed by the shear effect within the boundary layer tries to the fluid in the boundary layer has a tendency to get slowed down. Now when it has a tendency to get slowed down, still it has to move forward, then what is that which will try to make it move forward? One is the shear interaction with the outer layer, that is what it tends to make it move forward. So it has sort of it takes some energy from that and tries to retain its energy and make its forward movement, and if you have dp dx less than 0, that on the top of it helps it. If dp dx is equal to 0, then also it is okay, there is no extra effect from dp dx as a help, but there is no extra effect also in terms of resistance. But when dp dx is greater than 0, then the pressure gradient resists the forward movement. So there is a poor fluid element which is located within the boundary layer, has a tendency to get slowed down, and the pressure gradient externally on the top of it tends to slow it down further and further. So it has a tendency of continuous reduction in momentum, and that may give rise to a shift in the direction of the velocity. So that is how you can get a back flow or a reverse flow. So the momentum in the boundary layer is not sufficient, and external pressure gradient which is acting adverse to it if dp dx is greater than 0 may be just sufficient to make it flow in the reverse direction. But the question is, if dp dx is greater than 0, is it necessary that it has to flow in the reverse direction? The answer is no, it may not, because still it might have sufficient momentum to overcome that adverse pressure gradient and somehow maintain the flow, but if the pressure gradient is so adverse that it does not have enough momentum to overcome that, then only it will be a reverse flow. So existence of an adverse pressure gradient is a necessary condition for boundary layer separation, but it is not a sufficient condition. So you cannot say that there is a adverse pressure gradient and because of that there will be boundary layer separation, but you can definitely say that if there is no adverse pressure gradient there will be no boundary layer separation. So adverse pressure gradient is a necessary condition for boundary layer separation but not sufficient. The sufficiency will come from what is the strength of that adverse pressure gradient. Is it good enough to overcome the forward momentum and create a reverse flow? That is the important concept that we need to learn. So what we have understood is that if you have a flow, if you have a solid body in a fluid, the solid body in a fluid may be subjected to different forces, and these forces may come from, one is the skin friction drag which we have identified for flow over a flat plate even without pressure gradient, that is because of the shear, plus there may be a force due to the pressure gradient. So that force due to pressure gradient may give rise to a net effect which may also be a drag force, but to understand that what is the net effect, is it just a drag force or something more than that, we have to formally define that what are the forces which may act on a body which is immersed in a fluid. So let us do that. So we have now at least got the origin of the forces, that is the pressure gradient and the shear, but how we combine these to get the net force. So the resultant force on a body immersed in a fluid under motion. So do not confuse it with fluid statics, it is not fluid at rest. So we are not talking about forces like buoyancy forces like that. So this is solely because of the relative motion between the fluid and the solid, whatever is the force, that force we want to identify. So generally the convention is that, let us say you have an arbitrary shaped body, let us consider a two dimensional flow. So what are the forces which are acting on the body? One is there is a pressure distribution around the body. The pressure distribution is not uniform. Why it is not uniform? Because for example there may be flow separation. Because of the flow separation, after the flow separation has occurred it will be a low pressure region, and that means there is asymmetric pressure distribution that is created because of flow separation. So the net effect is that the pressure distribution will be non-uniform, there will be a force due to pressure distribution, plus there will be a force due to the viscous shear effect. So you will have some shear effect also, let us say that there will be some force due to shear. So you can see that even mathematically whatever we considered as tangential forces and normal components of forces, those are automatically coming physically through the effect of pressure as the normal force and the effect of shear through the tangential force. The resultant force, whatever, if you integrate the net effect over the body, you may resolve it into two components. What are, of course you may resolve it into two components in many ways, but what is the important convention? Let us say that this is the free stream direction, let us say this is the u infinity direction. So the force on the body, what is usually done is it is resolved into two components, one is in the direction of the free stream and another is perpendicular to the direction of the free stream, and let us say that this is the resultant force. So this force which is along the direction of the free stream is known as the drag force, and which is perpendicular to the direction of the free stream is known as the lift force. This is where we are talking about a two dimensional flow, but if it is a three dimensional flow there also may be a sidewise force in the third direction if there is also a component perpendicular to the plane where we are drawing the figure, but otherwise these two components must be there because the flow at least must be a planar flow, and these are very important because this drag force is something which will come in the form of frictional resistance, and the lift force is something which may give an upward motion to the body, and this is very important for wings of aircraft. So, if you have a aerofoil section like which represents the wings of aircrafts, then because of the lift force generated, it may go from a lower elevation to a higher elevation. So, both the lift force and the drag force are very important, and it is very important to characterize those. So, when we characterize the lift and drag force, we have seen that the drag force we may characterize by a coefficient of drag CD. So, the coefficient of drag is the drag force by half rho u infinity square into some reference area. We will discuss that what should be the reference area. Similarly, you have a coefficient of lift. This is the lift force divided by some half rho u infinity square. So, the coefficient of the lift and the coefficient of the drag are just non-dimensional ways of representing the lift and the drag force. So, when you have this drag force has two contributors, because see the resultant force along the direction of the flow is a resultant force due to shear having a component along the direction of flow plus resultant force due to pressure having a component along the direction of flow. So, when we have the drag force, its physical origin is divided into two parts. What are these parts? One is known as skin friction drag, which originates because of the shear, and another is known as pressure drag or form drag. Okay. Then from the name pressure drag or form drag, it is clear, first of all, why from the name pressure drag it is clear that it is because of the pressure distribution on the body. So, just like the skin friction drag is because of the shear force distribution on the body, the pressure drag is due to the pressure distribution on the body. Why it is also called as form drag? Because it is a strong function of the geometric form of the body, because the geometry of the body is what induces the pressure gradient. So, that is why it is called as a form drag. In engineering, one of the important objectives may be to minimize the drag force between a fluid and a solid, and if one wants to do that, then one has to see that which one is the stronger contributor, the skin friction drag or the form drag, and it all depends on whether the flow is laminar or turbulent. So, we will now try to look into the issue that first of all, if the flow is if we consider the skin friction drag, is it greater for a laminar flow or turbulent flow? If we consider a form drag or pressure drag, is it greater for turbulent flow or laminar flow? So, let us look into that. So, if we consider say a skin friction drag, skin friction drag depends on what? It depends on the wall shear stress distribution. Wall shear stress depends on what? One is the viscosity of the fluid, that does not change if the flow becomes turbulent from laminar. What changes is the velocity gradient at the wall. So, now you tell that if you consider the skin friction drag for a flow which is laminar and for a flow which is turbulent, then which should offer more skin friction drag? Obviously, that will have more skin friction drag for which du dy is more. If you consider mu du dy, the wall shear stress. So, which should have more du dy? Think of a situation. Consider that you have flow in a channel. If you have a laminar flow, what is the velocity, typical fully developed laminar flow velocity profile? Like parabolic distribution, right? This is what we have derived when we were solving this by using Navier-Stokes equation. But if it is a turbulent flow, of course, when it is a turbulent flow, we are drawing only the average component of the velocity. How it will look? See, for the turbulent flow, the important thing is that there is a great level of mixing in the turbulent flow because of the interaction between eddies of different scales. So, because of very efficient mixing between in the turbulent flow, the velocity, so mixing what it tries to do, it tries to homogenize it. So it will try to have a uniform velocity profile almost throughout, but at the wall it should satisfy the no slip boundary condition. So it should abruptly come down to 0 velocity at the wall. So the turbulent flow average velocity profile will be something like this, okay. So if you now consider that where du dy is more at the wall, for the turbulent flow, because here there is a high change in u within a very short y distance close to the wall. So this is the turbulent and this is the laminar. So we can see that since du dy at the wall for turbulent is greater than du dy for the wall for the laminar flow, considering all other conditions unaltered, and when we say turbulent du dy, you have to keep in mind this is the mean velocity that we are talking about. So that means you have the wall shear stress for the turbulent is greater than that for the laminar. That means you have the skin friction drag is greater for the turbulent flow, right. Now let us come to the form drag or pressure drag. When you come to the form drag, so for the form drag we are bothered about the geometry of the body. So the form drag, it all depends on the pressure distribution around the body. So form drag occurs because of what? Because of a boundary layer separation. Boundary layer separation will occur when the fluid in the boundary layer has insufficient momentum, so that adverse pressure gradient strongly overcomes that and creates a reverse flow, okay. So now in which case within the boundary layer you have more momentum, for a turbulent boundary layer or a laminar boundary layer? You expect a greater momentum in the boundary layer in the turbulent boundary layer, and since you have more momentum within the boundary layer for the turbulent boundary layer, you have a greater chance of resisting the adverse pressure gradient. Therefore flow separation may be delayed by virtue of having a turbulent boundary layer. So if the flow separation is delayed, what will happen? The separation point will shift to further downstream, and the pressure distribution which is there around the body, that asymmetry will be less and less. Therefore the drag force, because of the difference in pressure between the points which are located upstream and downstream of the separation, since the separation points shift towards the end, towards the downstream, then what happens? Then obviously you have a much smaller wake. Wake is the low pressure region beyond the separation point. So beyond the separation point, the region, if it is very small, then that is in a way better, because it will give rise to less form drag or less pressure drag. So if you have a turbulent boundary layer, it has greater momentum, it will delay the separation, and in the process it will have a less form drag. So the turbulent boundary layer has higher momentum, so it delays the separation, and that means it has less form drag or pressure drag. See, the engineering design has therefore a sort of conflicting things. So if you have a laminar boundary layer, you have less skin friction drag but a greater pressure drag or form drag, whereas if you have a turbulent boundary layer, it is the other way. Your question is not to minimize these individually, but the total drag force you have to minimize. So when you need to minimize the total drag force, you have to see which one is dominating, and when you see that which one is dominating, it depends on what is the shape of the body. If the shape of the body is such that it induces a separation much earlier, then the form drag is what dominates. If the shape of the body is such that it does not induce the separation so early, then the skin friction drag is what dominates. So let us look into some movies where we will try to figure out that what are the important characteristics of flow behind different bodies. So, if you look into this flow, this is flow past a cylinder, okay. So, if you consider this that circular thing as a cylinder where the length is perpendicular to the plane of the figure, if you play it once more, you see that after the separation, so the separation has occurred somewhere like maybe at somewhat in the middle section. Beyond that, you have the region in the back where you have these rotating structures and all, those are low pressure regions. So, but if you consider a different shaped body, you may also see a very similar thing. This is flow past a building. So, if you it is basically a building simulated, and if you see that there is a flow separation and there is a low pressure region in the back. So, whatever is the region which is towards the right after the boundary layer separation has occurred, that is a low pressure region, and it strongly depends on the shape. So, let us look into the case if you change the shape, what happens. Let us have a shape like this. So, if you see now, this is such a shape where the boundary layer separation is not there, it is almost avoided. It of course depends on that what is the direction of the relative velocity between the solid and the fluid, and that we will see, but just you can see that because of the section is such that it is not blunt, that you can see the previous bodies were sort of blunt, and those are technically called as bluff bodies. This type of a shape is called as a streamline body. So, a streamline body will have a much less tendency of boundary layer separation, and that let us try to see an example where we have a combination of streamline and bluff body. So, let us, so the sort of boat that is moving, it is like a streamline shape, and it is sailing fine in the water, but if you see now closely the flow around the starter, you see that this is quite bluff, and the flow around that is something which is having the effect of flow past a bluff body. So, I mean you may have combinations of bluff and streamline body together in the same effect, and if you want to see that what is the consequence in engineering design, we will of course we will try to understand this later, that what is the consequence in engineering design, but just to see that if you do not consider any boundary layer separation effect, boundary layer separation effect comes if you consider boundary layer effect. Now, if you do not consider boundary layer effect, it is like an inviscid flow, which is a potential flow. You see that case at the bottom, it does not show the boundary layer separation. At the top you see that you can get a boundary layer separation and you have a low pressure region, but if you design the car the back side like a streamline shape, then you may delay that separation and that will reduce the drag. So, you will see that many of the racing cars are designed in that way. So, to avoid or to minimize the drag force, we will come into these examples one after the other when we will look into in more details of flow past different shape bodies, but our important conclusion is that if you have bodies of different shapes, depending on that different drag forces may dominate. So, what are the important measures that you may take to delay the boundary layer separation, because boundary layer separation is an important issue that gives rise to a form drag or a pressure drag. So, what could be the measures? There are several measures which are possible. One of the measures is known as boundary layer suction. So, let us just note these down, that what are the measures, possible measures to delay boundary layer separation. Boundary layer separation. Number 1 is boundary layer suction. Boundary layer suction is what? Let us say that you have a solid boundary and there is a boundary layer that is formed. Of course, not for such a straight surface the form drag will be important. Let us say that you have a curved boundary, boundary layer is formed close to it, and somehow you what you do is you suck away fluid from the boundary layer into the solid. In the process what you do, you are basically increasing the momentum of the fluid within the boundary layer. So you are basically you are sucking the fluid from the boundary layer. So in the process what you are doing, you are enhancing the momentum of the fluid within the boundary layer. We have seen that one of the reasons of boundary layer separation is that the fluid in the boundary layer does not have sufficient momentum to overcome the adverse pressure gradient. So in this way, so we have looked into one example earlier in the previous class, say where you have some fluid which you put through the holes from the top and you suck that from the bottom. So this is one of the ways in which you can create greater momentum in the boundary layer. You could also do it in the other way, you might inject fluid into the boundary layer. So increasing the momentum is not so much dependent on this whether it is upwards or downwards. So you might have boundary layer injection. Then of course changing the shape of the body, that is streamlining the body. So if you have a bluff body, you may redesign it to make it of a streamlined shape, okay. Then maybe by artificially roughening the surface. If you roughen the surface, what happens? You may create sufficient perturbations to trigger the onset of turbulence. So roughening the surface artificially. These are some of the very practical things, and later on in one of our lectures we will see that sometimes the cricket ball is roughened in one side, what effect does it have on creating the swing in the cricket ball in a particular direction, and I mean these are some of the basic scientific tools that go behind. So we will just work out a problem quickly on the calculation of the resultant drag force on a body. So let us say that you have a circular cylinder with P infinity, U infinity as the free stream conditions, measure an angle theta from this direction, and it is given that boundary layer separation occurs. We will see that when boundary layer separation occurs in such a case in details later on, but say for this problem it is given that boundary layer separation occurs at theta is equal to 108.8 degree. This is from experiments. The wall shear stress is given by tau wall is equal to half rho u infinity square into Reynolds number to the power minus half into a function of theta, where the function of theta is equal to 0 for a range of theta between 108.8 degree to 180 degree, and integral 0 to 108.8 degree f theta sin theta is equal to 5.93. This is also from experiments. Also it is given the pressure distribution in a normalized way is given by P minus P infinity by half rho u infinity square is equal to g theta, such that integral 0 to 180 degree g theta cos theta d theta is equal to 1.17. This is also from experiment. So experimental pressure distribution and shear distribution is given as a function of theta. From that you find out what is the total, what is the net coefficient of drag. So you can clearly see that after the boundary layer has got separated, say 108.8 degree, beyond that you do not have a wall shear stress effect, because as if the effect of the wall has got detached from the boundary. So now how do you find out the resultant force? So if you just consider a small element located on the surface, let us say that you consider a small element d theta located at an angle theta. So the length of this one is what? Length of this one is r d theta. If you have a total force on this, you have one as the shear tau wall and another as the pressure. So what is the force due to the wall shear stress? dF due to the shear, so that is tau wall into r d theta into the length of the cylinder. That is number one, but what you want is the drag force, coefficient of drag. So you want the force component of this in the direction of the flow. So what will be that? So basically this into sin theta. So you will have dF drag due to shear is equal to tau wall into r d theta into L into sin theta. Okay. So you have the total drag force due to shear is equal to tau wall into r d theta L sin theta integrate 2 into 0 to 180 degree, right. Tau wall you know as a function of theta, and so you substitute that. So tau wall is equal to this into f theta. F theta sin theta d theta integral is already given to you. So you can substitute that here, it becomes a very simple calculation. Similarly, what will be F drag due to pressure? In place of tau wall, the effect will be because of P, and sin theta will become cos theta. So 2 integral P r d theta L cos theta from 0 to 180 degree. So the total drag is the sum of these two, that is the total drag. And what is the CD? CD is the total drag force divided by half rho u infinity square into reference area. For this kind of a case, so the circular cylinder is like this and flow is taking place across it. So the reference area is taken as the projected area perpendicular to the flow. So what is the projected area perpendicular to the flow? L into 2r. So this A reference, that is called as a frontal area or projected area, projected or frontal area, that is equal to 2r into L. So if you do that, let me give you the final answer which you may check. The final answer is 1.17 plus 5.93 divided by square root of Reynolds number. So what we can see here is that the drag coefficient at very high Reynolds number may be virtually independent of Reynolds number. And what are the important things that we see? This 1.17 is from where? This is from the form drag, this is from the skin friction drag. So very high Reynolds number flow may have the form drag is the sole determining factor for very high Reynolds number flow. So you can clearly see the effect of the form drag and the skin friction drag. So let us stop here today, we will continue again in the next class. Thank you.